Imagine a wire placed inside a changing magnetic field. By Faraday's law of induction, we get an electromotive force, a potential, that is voltage drop, that accelerates the charges and induces a current. The magnitude of this induced current is inversely proportional to the resistance of the wire. And that makes sense, because the less the electrons are slowed down by the atoms of the wire, the faster they'll flow.
But hold on, what happened if the wire atoms stopped resisting the electrons?
Oh shoot, if the resistance of the wire would be zero, then the induced current would be infinite, and that violates the conservation of energy.
Of course that doesn't happen. So materials with zero resistance, which we call superconductors, expel all magnetic fields from their inside, and that gives rise to strange effects like magnetic levitation. Isn't it beautiful?
So how does this work? Consider a metal. By the very definition of temperature, the atoms in its lattice will be wiggling and squiggling around, slowing down our electrons. As we make the metal cooler, the atoms in its lattice will appear almost static. Our negatively charged electron will attract the neighboring positively charged atoms, thereby distorting the lattice, creating a positively charged cloud. That cloud will attract another free electron, creating a bond between them, forming what scientists call a Cooper pair. The conglomerate of all Cooper pairs, by the rules of quantum mechanics, acts as one entity, meaning the electrons mutually drag each other along, and so the slowing down of one single electron by the vibrations of the lattice will no longer be possible. Hence, the entire conglomerate becomes unstoppable.
But not only metals exhibit superconductivity. In fact, the best, meaning highest temperature superconductors are ceramics, that is, insulators. And how exactly they work, that has yet to be discovered.